Welcome to this session of the lecture on the dielectric slab guide, which is a continuation of the previous lecture. In the last lecture, we discussed the electric and magnetic fields inside the dielectric region for the TM even mode. We will continue from there and we will find out the electric and magnetic fields in the air region for the TM even mode, for subsequent matching of the electric and magnetic fields across the dielectric air interface in order to evaluate the propagation constant of the TM even mode. So, in the air region, electric field E z is given by 1 by j omega epsilon naught k 0 square minus k z square psi a e, that is minus v square by j omega epsilon naught psi a e. Psi a stands for air, E stands for even, as before. Replacing now psi a e, we can write this as minus v square by j omega epsilon naught b e to the power minus v mod x e to the power minus j k z z from equation 21. We just substitute psi a e, we call this equation 24. Similarly, we can find out H y. Similarly, we can find out H y, the tangential magnetic field at the or in the air region. So, H y is given by minus del psi a e del x, that is equal to b v e to the power minus v x e to the power minus j k z z for x greater than a by 2 and H y equal to minus b v e to the power v x e to the power minus j k z z for x less than minus a by 2. So, we call this equation 25. So, now we equate the fields at x equal to a by 2. So, at x equal to a by 2, we have E d z equal to E a z. So, the electric field E z in the dielectric must be equal to the electric field E z in the air region at x equal to a by 2. So, therefore, we can write expanding E d z and E a z, a by j omega epsilon d u square cos u a by 2 e to the power minus j k z z equal to minus v square by j omega mu 0 equal to minus v square by j omega epsilon 0 b e to the power minus v a by 2 e to the power minus j k z z, which can be written as a by epsilon d u square cos u a by 2 equal to minus b by epsilon naught v square e to the power minus v a by 2. So, this is equation 26. At x equal to a by 2, at x equal to a by 2 we also have the equality of the tangential magnetic field components H y. So, we write at x equal to a by 2 we have H dy equal to H a y. Which implies a u sin u a by 2 e to the power minus j k z z that is equal to b v e to the power minus v a by 2 e to the power minus j k z z. That implies a u sin u a by 2 equal to b v e to the power minus v a by 2. Let us call this equation 27. So, we equated, we have equated the tangential electric field E z at x equal to a by 2 and the tangential magnetic field H y at x equal to a by 2. In order to drive out these unknown constants a and b, we will again take the ratio between 26 and 27. So, taking the ratio of 26 and 27, we obtain u by epsilon d cot u a by 2 equal to minus v by epsilon naught. Which implies minus u a by 2 cot of u a by 2 equal to epsilon d by epsilon naught V a by 2. Call this equation 28. In order to use the form of the function, the generic form of the function x cot x. So, this is the characteristic equation for determining the kz and cutoff frequencies of the even TM modes, because u and v can be expressed in terms of kz from the separation equation. So, equation 28 can be recast totally in terms of kz, replacing u and v, that will yield a single equation in kz from which kz can be obtained. So, this is the characteristic equation. This is the characteristic equation for determining the kz and the cutoff frequencies for the TM even modes. So, there is a complete duality between the TM and TE modes of the slab waveguide. So, the characteristic equations of the TE modes are just dual to those of the TM modes. We can write down the characteristic equation for the TE modes with odd psi. Which can be evaluated in exactly the same manner as we did for the TM modes with odd psi. So, for the TE modes with odd psi, we have u a by 2 tan u a by 2 equal to mu d by mu o times V a by 2. We mark this as equation 29. Compare this with 19. Compare with 19. Which is the characteristic equation for the odd TM modes. So, we see that epsilon d is replaced by mu d and epsilon naught by mu naught. So, for the T modes with even psi, after performing exactly the same analysis as we did for the TM modes with even psi, we will obtain the characteristic equation and that will be minus u a by 2 and that will be minus u a by 2 cot u a by 2 equal to mu d by mu naught V a by 2. So, this is equation 30. Again compare this with equation 28. So, you compare with equation 28 for the even TM modes. We see that epsilon d is replaced by mu d and epsilon naught by mu naught. We should also note that the odd functions generating the TE modes or the odd potential functions generating the TE modes are given by the same equations as the TM modes, which are equations 5 and 6 and similarly the even functions which are generating the TM and similarly the even functions generating the TE modes are given by exactly the same equations from which the TM even modes are obtained, the same potential functions from which the TM even modes are obtained, and those are equations 20 and 21. So, the fields are obtained from the psi's by equations which are dual to equation 4. So, for the TE modes, the fields are obtained from the psi's by the equations which are exactly dual to equations 4 that are relevant for the TM modes. We have already derived those equations, but these equations are for del y equal to 0 and del z equal to minus j k z as we did for the TM modes. So, for the TE modes, the fields are obtained from the psi functions as h x equal to minus k z by omega mu del psi del x, h z equal to 1 by j omega mu k square minus k z square psi, and E y is given by del psi del x. So, let us call these sets of equation as as 31. Now, because the dielectric guide is an open structure, the concept of cutoff frequency for such guides is somewhat different compared to metallic guides, where the fields do not escape from inside the metal. So, what is happening here? So, we have the fields which are sinusoidally or co-sinusoidally dependent on the x coordinate inside the dielectric slab and which are exponentially decaying above and below the dielectric slab. So, under such a condition the guidance takes place inside the slab. So, we say that above the cutoff frequency the dielectric guide propagates a mode unattenuated, that means Kz, which is the propagation constant along the z direction, is real. So, we write above the cutoff frequency Kz is real. However, below the cutoff frequency Kz becomes equal to beta minus j alpha. But since the dielectric is loss free, this attenuation of the wave, which is the complex part of Kz, is due to the radiation of energy in the air region as the wave propagates inside the dielectric. So, as the wave propagates inside the dielectric, it progressively loses energy in the air region. This condition is what characterizes the wave below cutoff. So, this is saliently different from metallic waveguide, as we saw, where there is no radiation of electromagnetic waves, because the waves are only contained between the metallic walls of the guide. So, therefore, the dielectric guides operating below cutoff can be used as antennas, because they are radiating energy to free space, and therefore, I can make the same dielectric strip or dielectric guide operate as a guided wave medium with Kz real above cutoff, which are essentially called surface waves inside the dielectric, or I can make it work as an antenna, so that these waves have complex propagation constant, and therefore, as they proceed or as they progress inside the dielectric slab, they progressively lose energy in the air region. This in fact marks the below cutoff region of the dielectric slab, where the dielectric slab can be used as an antenna. It is very important to understand, therefore, that a lossless dielectric slab can have an imaginary propagation constant. This is a very important thing to appreciate, that the dielectric strip, though perfectly assumed lossless, can have an imaginary propagation constant, and this imaginary propagation constant is due to the radiation of electromagnetic waves in the air region as the wave, the T or Tm mode, progresses inside the dielectric slab. Now, the question is, what demarcates the cutoff and what demarcates now the question is, what demarcates below cutoff and above cutoff. So, the phase constant of an unattenuated mode. So, if the mode is unattenuated, which means that Kz is real for this condition, which is an unattenuated mode, it lies between the phase constant of the dielectric and that of the air region. So, the propagation constant or phase constant of an unattenuated mode will lie between the intrinsic phase constants of the dielectric and the air region. That is, we will have k 0 less than, that is we will have k 0 less than k z less than k d. 32. We go back to equation number 7. We see that k z is less than k d, because u square plus k z square is k d square. So, k z is less than k d. Now, if k z is greater than k naught, then V is real. So, k z square minus V square is k naught square. So, therefore, if V is real, then the distribution of fields in the air region is exponentially decaying, or it is of the exponentially decaying type. So, have this very clear picture in mind, that when a wave propagates inside the dielectric slab above cutoff, or when the dielectric slab is being operated above cutoff, the waves in the air region are of the exponentially decaying type, while k z is real. This condition is mathematically the same as this condition, that k z will lie between the intrinsic phase constant in the dielectric region, which is k d, and the intrinsic phase constant in the air region, which is k naught. So, the lowest frequency for which the unattenuated propagation exists is called the cutoff frequency. This we have borrowed from the concept of cutoff frequencies in the waveguide. So, the lowest frequency for which k z is real, we call it the cutoff frequency. So, therefore, cutoff occurs as k z tends to 0. Cutoff occurs for the dielectric slab as k z tends to, cutoff occurs for the dielectric slab as k z tends to k 0, because if k z becomes lesser than k 0, then V or the eigen number or the eigen value in the air region is going to be complex. So, if k z is lesser than k 0, V or the eigen number in the air region will become complex, and therefore, we will have propagation in the air region, not evanescence in the air region, not exponentially decaying waves in the air region. We will start to have propagation in the air region, because V will turn out to be complex. So, it will be instead of e to the power minus V x, e to the power minus j V prime x. So, there will be propagation in the air region. So, therefore, the dielectric slab is going to radiate in the air region. Therefore, its energy will reduce as it propagates inside the lossless dielectric strip. This condition or this behavior of the dielectric slab will occur below cutoff, when the dielectric strip will therefore behave like an antenna. So, k z approaching k 0 is the same as V approaching 0, and therefore, the cutoff frequencies can be obtained from the characteristic equations by using or by setting u equal to root of k d square minus k 0 square. Because k z is tending to k 0, therefore, look at equation 7, u will be equal to root of k d square minus k 0 square and v equal to 0. So, this constitutes the cutoff frequency of the dielectric slab guide. And when we do that, when we substitute them in the characteristic equations, we obtain 10 a by 2 root of k d square minus k 0 square equal to 0. So, we can look at equation number 19 and substitute u equal to root of k d square minus k 0 square. Since v tends to 0, the right hand side of 19 tends to 0, and because u cannot be 0, u a by 2, and because so this equation can be obtained from equation 19. When we look at equation 19, we substitute v equal to 0. So, the right hand side of equation 19 becomes equal to 0 and we obtain the condition 10 u a by 2 equal to 0, substituting u equal to root of k d square minus k 0 square. Similarly, we can look at equation number 28 and from there we will obtain the condition cot of a by 2 root of k d square minus k 0 square equal to 0. So, this is for the odd TM mode, this is for the even TM mode. And the same equation holds good for the TE modes, because the characteristic equations are the same, only change is replacing epsilon by mu. So, these applies to both the TE and TM modes. So, these equations are satisfied when a by 2 root k d square minus k 0 square equal to, these equations are satisfied when a by 2 root of k d square minus k 0 square equal to n pi by 2 for n equal to 0, 1, 2, etc. For n equal to 0, 1, 2, etc. Or we can write a by 2 root of omega square epsilon d mu d minus omega square epsilon naught mu naught equal to n pi by 2. Which can be written as a by 2 replacing omega by twice pi f and f c, where f c is the cutoff frequency, root of twice pi f c root of epsilon d mu d minus epsilon naught mu naught equal to n pi by 2, which implies f c as equal to n by twice a root epsilon d mu d minus epsilon naught mu naught. Let us call this equation 33. The corresponding cutoff wavelength lambda c becomes equal to c by f c, that is equal to 1 by root of epsilon naught mu naught twice a root of epsilon d mu d minus epsilon naught mu naught by n, or that can be written as twice a by n root of epsilon d mu d by epsilon naught mu naught minus 1. We call this expression for the cutoff wavelength lambda c as equation 34. So, the modes are ordered as T m n, the modes are T m n and T e n. So, these are the modes in the dielectric slab or called also the dielectric slab modes. Okay. So, we should also note that the f c or the cutoff frequency corresponding to the T e 0 and the T m 0 modes. So, for the T e 0 and the T m 0 modes for n equal to 0, the corresponding cutoff frequency is 0. So, the T 0 and the T m 0 modes in the slab possess a 0 cutoff frequency, that is they propagate right from DC. Okay. So, this concludes the session on the evaluation of propagation constant inside substrate based structures or the dielectric slab. So, we now have a much more useful, a physically meaningful insight for the design of substrate based circuits and antennas. Okay. We have a clear understanding of what is meant by propagation in a dielectric slab, what is meant by cutoff in a dielectric slab, what happens in propagation, what happens in cutoff, what are the relevant mathematical parameters characterizing the propagation region and the cutoff region, which is invaluable for the understanding of any kind of substrate based circuits. Thank you for your attention.